Hello students, welcome to IMS Gate Academy. In today's session, I would like to do questions from the GATE 2023 EDC questions. I selected EDC questions from the GATE 2023 papers that I will discuss. But each and every day you can have the what now? Session there. I will discuss the GATE 2023, 22, 21, like that 5 years papers I will do now, understand now. Okay, I will give the questions and you can also try the questions what I am going to give here now. You please try this question, understand now. In a semiconductor, the question was given like this. In a semiconductor, if the Fermi level energy, if the Fermi level energy lies, I will explain each and every point, lies in the conduction band, then semiconductor is known as, here given 4 options, those 4 options I will give. Option A, degenerative, N type. Option B is given here, degenerate P type, Option C is given here, non-degenerate, N type. Option D is given here, non-degenerate P type. Yes, these are the 4 options are given for this question. These are the 4 options are given. Anybody can give answer. This is a GATE 2023 paper. 2023 questions from the what? EDC, from electronic devices and circuit. Any student can give answer for this question? Any student can give answer for this question? Anybody? Anybody can give answer for this question without my help? Initially, I want to get answer from your side. If I get it, very happy. Anybody? Yes. In the problem, what is given, you please watch. I will explain clearly. You will get idea. In a semiconductor, if the Fermi level energy lies in the conduction band, the Fermi level is lying in the conduction band is given now. So what I wish to say, otherwise I will write in the next paper best. You will get the clear clarity. You will get clear clarity. I am giving the solution now. For the semiconducting material, energy band diagram is plotted in this way. This is to be taken as a conduction band this is taken as valence band. This is taken as a valence band. Like that, we can keep it here now. One is a valence band, one is a conduction band only now. But if it is a intrinsic semiconductor, catch my point. If it is an intrinsic semiconductor, Fermi level can lie exactly, that means approximately at the center only. We know very well. If it is an intrinsic, pure type of semiconductor. But if it is a P type, whether it is a P type or N type, first we need to identify. Because in the options you watch what is given here, you try to catch, you can understand. In a semiconductor, the Fermi level energy lies in the conduction band. Fermi level is lying in the conduction band only. Then semiconductor is known as what? Type. N type or P type or N type and P type also given like this now. But in the first, what is the type of the what now semiconductor we can try identify. Then after, is it a degenerate or otherwise what non-degenerate, we can identify clearly now. So how we can identify that means, please watch it now. The Fermi level is exact, but now approximately it is lying at the center means I said it is an intrinsic semiconductor, no doubt. If the Fermi level is lying very close to the valence band, you think it's so. The Fermi level is lying very close to the valence band. Even it is lying inside of the valence band, we can say it is a P-type extrinsic semiconductor. It is a P-type extrinsic semiconductor. When I can say it is an N-type extrinsic semiconductor, if Fermi level energy is lying very close to the conduction band or even it is lying in the conduction band, we can say it is an N-type only now. That means Fermi level is going towards the direction of the conduction band, it is an N-type. The Fermi level is going towards the direction of the what now valence band, we can call it as a what now P-type extrinsic semiconductor. But in this problem, the Fermi level lies in the conduction band is specified clearly. It is lying in the conduction band. If it is lying in the conduction band, catch my point. If it is lying in the conduction band, it's just towards conduction band you got. If the Fermi level is lying in the conduction band, 100% it is nothing but N-type extrinsic semiconductor. It is an N-type extrinsic semiconductor. And next one, it is given, is it degenerate or non-degenerate extrinsic semiconductor is very important. Sorry. When we can say it is a degenerate, when we can say it is a non-degenerate, that is very important now. Suppose in a semiconductor doping is made, not highly, light doping is made. Light doping whenever you made, then it comes under non-degenerate type only now. It's a non-degenerate. Whenever you are adding the what now more concentration of the doping of the more you added, you think it's so. At the time it is said to be what now degenerate semiconductors only now. Here conduction band is lying in the conduction band is what the Fermi level is lying in the conduction band means 100% it is a what degenerate. It is a degenerate only. It is a degenerate only. High doping is made. It is lying in the conduction band. If it is lying in the conduction band, it is a degenerate. If it is below the what now conduction band, you think it's so below the conduction band. You can say it as a non-degenerate only. You can say anyhow it is lying in the conduction band. That's why it is a degenerate. It is towards the direction of the conduction band. 100% is an N-type extrinsic semiconductor. Finally, we can say the type of semiconductor is degenerate N-type extrinsic semiconductor. You can say it now. And option A is correct only now. We can go to next question. Yes, I would like to do the next question, which is asked in the gate. Next question I want to give in your hand. You please try this question. I want to give in your hand only now. For an intrinsic, semiconductor, an intrinsic semiconductor at temperature at temperature T equal to 0 Kelvin, 0 Kelvin is given. Which of the following, which of the following, which of the following, which of the following which of the following statement is true? Statement is true. True it is given. And 4 options are given now. I will explain clearly now. You will understand easily now. First, let me write all the conditions. All energy states, all energy states in the valence band, in the valence band, clear clarity I will give, valence band are filled with, are filled with electrons, electrons, and all energy states, and all energy states, all energy states, all energy states in the conduction band, in the conduction band, in the conduction band are empty of electrons, are empty of electrons, empty of electrons. Option B is given. I will give the 4 options that I will give you now. All energy states, all energy states, all energy states in the valence band are empty. VB I will put now, valence band, that is best instead of writing the valence band are empty of electrons, are empty of electrons, ES I have taken now, electrons, empty of electrons, and all energy states, and all energy states, all energy states, all energy states in the conduction band are, in the conduction band are filled with electrons, filled with electrons is given now, filled with electrons. That is option B. But option C is given here, all energy states, all energy states, all energy states in the valence, in the valence, in the valence and conduction band, and conduction bands are filled with holes, are filled with holes I can say, are filled with holes. And option D is given, option D is given, all energy states, all energy states, all energy states in the valence, in the valence and conduction band are filled with electrons, filled with electrons, filled with electrons. These are all the 4 options are given here now. I would like to explain clearly. You will understand that. You will understand clearly now. But anybody can give answer for this? Initially, I want to give in your hand only now. You please try to give answer for this question. Any student can give answer. Can you respond? I'll see any student will give answer or not. If you give answer, very happy. Anybody? Anybody can give? I will give the time, 2 minutes to take it and give answer. You please take time and give answer for this question. Anybody can give answer? Okay, I will explain. Please watch. Clear concept I will give. But this question also asked in the GATE 2023 in EDC. This question was asked in EDC only now. For an intrinsic semiconductor at temperature T equal to 0 Kelvin, you know very well, intrinsic semiconductor means it is a pure type of semiconductor. The given semiconductor is a pure type. That means no doping is made. At the time I can call it as intrinsic semiconductor. At T equal to 0 Kelvin, which of the following statements is true? That is our question only now. And 4 options are given now. You go, all energy states in the valence band are filled with electrons. That means the valence band is filled with electrons only, it is given now. And all energy states in the conduction band are empty. Valence band with electrons and conduction band empty. The first option is given. Option B, all energy states in the valence band are empty of electrons. That means no valence band and conduction bands are with no electrons only. It is given. Second one. Option C, all energy states in the valence and conduction bands are filled with holes. That means the valence band and conduction bands are filled with holes only. He says option 3. What about option 4? All energy states in the valence and conduction bands are filled with electrons. But all the in the valence band are empty electrons, and all energy states in the conduction band. Okay, in the valence and conduction bands are filled with electrons only. It is given now. So these are all the 4 options are given. I will give the clarity. You can understand now. You will understand clearly now. The point what I wish to say is, it is an intrinsic semiconductor. It is given clearly. It is given for intrinsic semiconductor. For intrinsic is the solution. For intrinsic semiconductor. For intrinsic semiconductor, energy band diagram I can plot in this way. This is said to be conduction band. This is said to be valence band. This is said to be valence band. You know very well, this voltage is nothing but EV. This voltage is nothing but the EC only, we can say. In the intrinsic semiconductor, the Fermi level energy is going to lie approximately at the center, you know very well. EFI, Fermi level energy in intrinsic semiconductor. The valence band, but valence band is with number of covalent bonds. Valence band is only with number of covalent bonds it can exist. That means what now? Electrons are existing, they are within the bond, in the what now? Valence band, not band. In the band theory, I am explaining now. The outermost orbit, electrons are nothing but the valence electrons only now. Those electrons are what now? Within the attractive force of the nucleus. Within the attractive force of the nucleus only now. That means they are bound by the what now? Nucleus only now. Anyhow, the valence band is with number of covalent bonds. Electrons are existing within the bond. That means all the electrons are in this band only now. When we can find electrons in the conduction band, you must give temperature only now. The temperature is not given, the temperature is maintained 0 Kelvin only, because the question is at 0 Kelvin only now. At 0 Kelvin, what is going to happen now? The bonds will not be broken down. The bonds will not be broken down. But whenever you are maintaining the room temperature, immediately what is going to happen now? Bonds will be broken down in the valence band. Once the bonds are broken, what is covalent bonds are broken, multiple number of electrons are going to generate. If the number of electrons are generated, what is going to happen? Now, directly they will try to move from valence band to conduction band. Once the electrons are liberated from the valence band, you think is so, they are not going to stay within the forbidden energy gap. This gap is a forbidden energy gap. They are not going to lie in the forbidden energy gap. Once the electrons are liberated, directly they will enter into the conduction band. They are going to stay there only now. At room temperature, it is possible here now. But at 0 Kelvin, what we are finding now, no covalent bonds are broken within the valence band. At the time, no electrons are generated. At the time, no electrons will be reaching to the conduction band. So, conduction band is empty at 0 Kelvin. Catch my point. At T equal to 0 Kelvin, what I can say, 0 Kelvin, conduction band is CB, conduction band is empty. It is empty only though. It is empty. But where electrons are existing within the bond, that means in the valence band only. That means the electrons are going to exist in the valence band only now. Electrons are existing in valence band. In valence band. In the valence band means they are lying in the bond only now. Within the bond only it is going to exist only, you can say. Finally, which option is correct? You check it based upon that point. That means in the first option you watch now, what is given? All energy states in the valence band are filled with electrons. Yes. At 0 Kelvin, electrons are within the valence band only now. They are lying within the bond only now. That's why we can say it is within the filled with electrons only now. And all energy states in the conduction band are empty of electrons. We don't find any number of electrons. That means all the electrons in the conduction band are empty is specified only now. So 100% option A is correct only, we can say. This option is satisfying only now. But in the second option you watch valence bands. Valence band are empty of electrons and valence band is not empty of electrons. Impossible. We cannot find. Bonds are not broken down. We cannot say it is an empty one. Even third one you watch it now. Valence and conduction bands are filled with holes. How? Electrons and conduction band and valence band both will not be with holes. Impossible. At any cost we cannot find practically. All energy states in the valence and conduction bands are filled with electrons. No. Electrons, valence band and conduction band are filled with electrons. When it can fill with electrons in the valence band and conduction band, when you are maintaining temperature of 300 Kelvin, then only you can find electrons in the valence band and conduction band only. But we are not maintaining 300 Kelvin now. We are maintaining only 0 Kelvin. At the time, we cannot find any electrons in the conduction band. So option A is correct, we can say now. Such a way, we need to do this question now. I hope you followed. Any students are having any doubts regarding this question? Anybody having any doubts? Can you respond? If you responded, it's very good now. Any student? Yes, I want to give one more question, one more gate question. But I want to give next question. But it's going to take to write the question only now. Just I'll write this question, you'll understand now. Yes, next question is given like this in the gate. Yes, Samrat Rajput. Samraj Rajput. No, no means what? I don't understand. Samrat, can you say? What is no means? May I know? Do you face any problem at anywhere? If it is so, I can clarify, no problem. No doubts you are saying at least, Samrat? Samrat Rajput, did you understand or not? Please respond. Please respond. Did you understand, Samrat? followed or not followed? Samrat, Rajput, can you respond? Shall I go to the next question? Yes, I'll give you the next question. For MOS capacitor, is there any problem? Samrat, is there any problem? So I said no. Oh, any problem? Oh, do you have any problem? I asked, is it not? Yes, you followed, then I did not. Very good. Thank you then. Yes, I only asked, correct, exactly. Clear, is it not? Very good, very happy. The doubts are cleared means very happy. Next question. For a MOS capacitor, VFB and VT are the flat band voltage, the flat band and threshold voltage. Come on. Voltage respectively. The variation of the depletion width W suffix DEP for varying gate voltage VG is best represented by and 4 options are given. I will give the options, easily you can identify which option is correct. This is VG and this is a WDEP and this is given such a way. This voltage is given VFB, flat band voltage. This is given VT. This is accumulation, it is given. Accumulation. The depletion is given. This is inversion. Option B is given here. Like this. This is the gate voltage. The diagram goes like this. That's given. This is W suffix DEP. This voltage is given VT. This is a VFB, flat band voltage. And option C is given here. Option C is given like this. Very easily you can understand. This is a VG gate voltage, W suffix DEP. This diagram is given like this. This is a VT value and this is a VTH, it is given. VTH is given. Sorry, VFB, sorry. This is given VFB. This is given as a VFB. And the option 4, option D, this is a gate voltage, here given diagram like this, W suffix DEP. Here given VFB, this voltage is given as a VT1 now. Yes, these are the 4 options are given. These are the 4 options are given. Choice, sir, would be better if you don't write the question and instead just set the question. Yes, what you said is a correct one now. From the next class I will do now. Please get adjusted this time, understand now. This time, next time onwards I will use the directly PPTs I will use the now, understand now. It is a wasting time for you also now, understand. It is going to give some bore also now. What you said is a true. Okay, this time you try to excuse it, understand now. Shall I do? Shall I do? Merry life, merry choice. Shall I do? Anybody can give answer for this question without my help? Yes, Manoj Kumar says option B is correct. Option B is correct, he says, Manoj Kumar. What about other students? May I know? May I know about other students? But the question is asked in the gate, no doubt. Same 2023 in EDC, no doubt. The required information I will just pass. The students easily, they have to understand only. I will not go much depth only here now. But the question from the MOSFET, everybody knows. This is from the MOSFET only now. But the W suffix DEP and VG diagram is given here now. Can you please explain? Yes, that all I am doing now. That all I am doing now. No doubt. That I am doing now. I can't recall. Okay, okay, no problem. But in this case, for MOS capacitor, the four options are given anyhow. In this 4 option, which is right means I will give the clarity. I will give the clarity. Here the accumulation mode, depletion mode, inversion mode, 3 modes of operations possible for the MOS capacitor. Any MOS capacitor you got means that can have accumulation mode, depletion mode, inversion mode, they will apply. But when the accumulation mode means for this you are going to apply the negative potential only. Gate potential is given negative only now. Gate potential negative only. Depletion mode they are going to give the what now positive value. The smaller potential they will give. Inversion mode means they will give the more positive potential they are going to give only now. By changing the gate potential, W suffix DEP width is required. That means in the MOS capacitor means you know very well. It comes shaped like this. You'll get idea. The MOS capacitor is, you can have metal, conductor, metal. Next one, you are going to have the oxide, metal, oxide, SiO2, oxide, SiO2, silicon dioxide, mostly possible. That's possible. This is said to be bulk. This is a bulk or body you can call. This is the gauge. This is the gate they are going to call. This is a semiconductor, no doubt. Semiconductor they are going to use. Suppose I am using here the p-type extrinsic semiconductor. P-type semiconductor I am using here now. P-type semiconductor suppose I am using. The gate is given a negative potential. Negative potential is given. Negative is given means what is going to happen? Negative, P-type is a positive. The holes are the what now? Majority carriers, they will be attracted here now. Positive charges will come. That means these are the charge carriers are not going to down, they are going to be attracted towards this direction only now. In case you are giving the what now? Gate potential of positive you are giving. Positive, suppose you gave it now. Positive whenever it is given, this is a positive, P-type semiconductor, positive, 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 repulsion. Due to repulsion, holes will try to move up to some distance. the distance is a W due to depletion only now. Depletion of the charge carriers possible because the same positive potential, positive repulsion, they will try to move. Positivity is given now. Some W width is possible now. W DEP. VG is given more potential. VG is given more potential. It will try to move up to some extent only now. Yet the point what I wish to say is easily you can understand. Whenever you are maintaining, when gate potential you are maintaining threshold voltage. Gate potential is maintained threshold voltage. I am not going in depth this there now. If it is done means it is a 3 hours or 4 hours class is possible now. Here we need to complete very fast now. Gate potential, if I maintain threshold voltage, what is going to happen now? There only you can find maximum, this is the distance, what distance it is moved is nothing but X DEP. It is going down only now. Positive repulsion, they will go up to some depth, X DEP. There's a X DEP is nothing but X DEP or X maximum only possible. X DEP maximum. Maximum what now? Depletion is done. At threshold voltage only, you can find maximum depletion only. When the gate potential is applied more than the what now threshold voltage, you think it's so. It doesn't have any more changes. The depletion is the maximum. It will never go beyond this level only now. Now the point what you have to remember, whenever the X DEP equal to X maximum is nothing but what I can say, W maximum only. The point what I said, when the maximum W suffix DEP is possible or X DEP is possible, whenever the gate potential is maintained, threshold voltage, catch my point, threshold voltage, then maximum is possible. Where you can find, but in this case, before the threshold voltage only, maximum I am getting W suffix DEP. This is not acceptable, not allowed. Second one, you watch it here now. When threshold voltage is maintained, VG equal to threshold voltage I maintained maximum, W suffix DEP I got now. That means after that it is going to remain constant only, I said now. After threshold voltage, we cannot find any variation now. Maximum depletion of the charge carriers are possible exactly at the threshold voltage only now. So after that voltage, you can it will be maintained constant only possible now. So 100% this is correct only. Even third one you watch, it is impossible. At the threshold, what that means at T, when VG equal to 0, I am getting the what now? Maximum voltage. No. At threshold voltage only maximum W suffix DEP required. This is also not correct. But if it is taken, even VG equal to 0 only, I am getting the maximum. 100% this is also correct. Incorrect. Finally, it is incorrect. Finally, which option is correct? Option B is correct. When gate potential is maintained as a threshold voltage, at the time we are going to get the what now? W suffix DEP of maximum only now. But after that, even the gate potential you are increasing, the variation is not possible. That is going to remain constant only now. That is according to the MOSFET only now. We can't go more than that level. Gate point of view, I gave it now. Understand? Yes, we can go to next question. Next question I will give. The one more gate problem is given, one numerical problem is given, the gate. I wish to give in your hand. One numerical problem is given. In intrinsic, in extrinsic, in extrinsic semiconductor. Okay, this time you please accept what now, without PPT. The next class onwards I will start use the PPT. 100% time we can save. Extrinsic semiconductor, the whole concentration is given to be 1.5 Ni. where Ni is the intrinsic carrier concentration, intrinsic carrier concentration of 1 into 10 power 10 per cm cube it is given, per cm cube. The ratio of electron to hole mobility for equal, okay, color is changing, just wait 1 minute. For equal whole electron drift current is given as dash round off to 2 decimal places. I will not give anything, round off to 2 decimal places. Anybody can do this question without my help, but I want to give time. Please do it, but I want to give you time, some time I want to give now. Can I do this question without my help? But I want to know how students can do this question. Anybody? This question also asked in the GATE 2023 in EDC only now. Yes, I will do, please watch. It is an extrinsic semiconductor, no doubt, clearly given in the problem. It is extrinsic semiconductor, yes. The whole concentration is given to be 1.5 Ni. That means the concentration of the holes are given where in extrinsic semiconductor. Holes means P. Holes are the P. In which type? P-type extrinsic semiconductor only, because the holes are the majority only. Holes concentration is given. I wish to select P suffix P is given, holes concentration is given in the problem. 1.5 into Ni. 1.5 into Ni is given. And Ni is the intrinsic concentration. Intrinsic concentration also given. 1 into 10 power 10. 1 into 10 power 10 per cm cube it is given. Per cm cube is given. 1 into 10 power 10 per cm cube is given in the problem. Intrinsic concentration is given like this now. And also in the problem, what is given here now? The ratio of electron and hole mobility is required. Electron and hole mobility means what is mu n by mu p is asking to find. What that ratio is asking to find. And still what is given in the problem? Electron hole mobilities of for whole electron drift currents, it is given. Equal whole electron drift current is given. Drift current due to the electrons and drift current due to the what now? Holes. Drift current due to the electrons and drift current due to the holes given here equal only now. Those two values are given. At that condition, we need to get answer only now. I will do, you watch this question, easily you can understand. Easily you can understand. Nobody is going to face any problem in doing this question now. In a problem, what is given here? Hole concentration given. Solution I want to take. Hole concentration is given in the problem. The hole concentration I wish to denote by symbol P suffix P. Number of holes in P-type extrinsic semiconductor is extrinsic semiconductor only. That is nothing but 1.5 times of Ni is given. And also in a problem it is given intrinsic carrier concentration equal to how much it is given. Ni is given as a 1 into 10 power 10 per cm cube is given. per cm cube is given. The ratio of electron to hole mobilities, I want hole mobilities, electron to hole mobilities I want, mu n by mu p I want. Mu n by mu p equal to how much is asking? That is the question. When electron and hole drift current is equal. Catch my point? Yes, somebody gave now. Sir, please arrange a RIXI class for EDC of 6 to 7 hours. Yes, I can discuss now with the management now. Sure, 100% now. They will conduct so many classes like that only now. There I will do the all the topics easily to understand only now. But in depth I will give clear clarity now. Understand now. You will follow 100%. Your point will be considered now. I will inform to the management, no doubt. Yes, you please watch. Here the drift because our drift currents are equal, it is given now. For drift you must understand. For drift you must understand one point. The currents of drift, hole current and electron drift currents are equal. IN equal to IP. Because the drift, IN and IP are equal, it is given now. When those two are equal, you need to calculate the that ratio only now. But what is IN, what is IP is more important. In electronic devices and circuits, you know very well about the IN and IL values now. Those values are given like this now. IN value is nothing but direct formula is there now. But IN value is taken as, you clearly now. Yes, electrons means I can write N into Q into mu N into E into A. Current due to the electrons is N into Q into mu N into E into A only now. That formula you know very well. In the EDC mostly it comes. One derivation is there now. Here not possible to derive. IP means in the place of N is the concentration of electrons. Okay, it is an n-type material, Nn I can put otherwise. Np I will use because in the p-type semiconductor, electrons concentration. IP is nothing but the holes concentration, the p-type semiconductor. Q into mu p into E into A. The drift current due to the electron is taken this. The drift current due to the holes will be taken by this formula. A is the area of the cross section, E is the electric field intensity, mu p and mu n are nothing but the mobility of electrons and holes, Q is the charge, Pp is nothing but the concentration of the holes in the p-type, Np is nothing but the concentration of the holes in the p-type, concentration of the electrons in the p-type semiconductor. The point what you have to remember here now, Ea and Ea this side and this side I can cancel. I can cancel these two sides. This and this I can cancel. And charge also I can cancel directly. And finally here what I am getting here now, mu n by mu p I want mu n by mu p. I want mu n by mu p. Mu n by mu p equal to what I can use here now, mu n by mu p is to be taken as a p suffix p by what I can take, n suffix p I can use, n suffix p I can write here now. But thereby required p suffix p and n suffix p only now. Here we know p suffix p is given 1.5 times of Ni. I am not substituting this Ni value, it is base. Finally Ni will be cancelling, no doubt. You watch how it is cancelled now. Pp is nothing but 1.5 into Ni, we know very well. 1.5 Ni value. What about n suffix p? But it is a p-type extrinsic semiconductor. In the p-type semiconductor, electrons are the minority carriers now. Minority carriers in the semiconducting material is calculated by mass action law only now. Without applying the mass action law, we cannot get the minority carriers now. We know very well. According to the mass action law, what formula you can apply? Concentration of the electrons means now Ni squared by what? Ni squared by P. P means Ni squared by P suffix P it comes now. P suffix P. Ni squared by P. Square of the intrinsic concentration by holes concentration only now. But a p suffix p we got already. How much p suffix p? 1.5 into Ni. I will substitute there now. 1.5. And finally this value I can write. I will write in the next page. Mu n by mu p is nothing but what I can write here now. There I can write 1.5 into and here given This is a P suffix P is nothing but how much? 1.5 into Ni, 1.5 into 1.5 Ni, 1.5 square Ni square. 1.5 square into Ni square I am getting here now. Divide by what I am getting here now? Divide by Ni square is there now. Divided by Ni square. I can cancel Ni square and Ni square. Finally, 1.5 whole square I can get now. 1.5 square is nothing but 2.25 only possibles. That way, the ratio of mobility of electrons to the mobility of holes calculated only now. Such a way we can calculate. I hope students followed this. Did you understand or not? Anybody? Anybody having any doubt regarding this question? Regarding this question, anybody has got any doubt? Please respond. You should know here only one point. When the drift is taken place, because the drift current is going to flow, that is due to electrons and holes. So, IN equal to IP is given in the problem. IN and IP you equate it. What is IN and what is IP formula you must know. Using that you can get directly. Followed this? Yes, I hope you followed this now. Understand? But you can close it now. Thank you now. The next class we can see to the questions now. Bye.